All right, everybody, welcome to Math with Grace. Today we're going to be working through Pre-Calculus, Unit 7, Section 1. Section 1 begins on page 5, and it's titled Polar Equations. Now, what we're going to be working with in this section is the polar coordinate plane. This is not it. You'll see it when we turn the page. But it's not too complicated. So let's take a look at how it works together and then see if we can do some of these problems. So it says graphing system uses a grid comprised of concentric circles with rays emanating from the center. That's the polar coordinate system. Like I said, this is the regular coordinate plane, right? The polar system uses concentric circles all centered on the origin and then a ray coming out from there. It says the polar system has a pole and a polar axis. For reference, the pole is the equivalent of the origin. The polar axis is the equivalent of the positive x-axis. In the polar coordinate system, a point is located using the ordered pair r, theta, where r is the distance from the pole and theta is the measure of the angle from the polar axis. Okay, polar axis. Concentric circles. Let's turn the page and actually look at what that looks like. So the top of page 6, we get our actual first look at a polar coordinate. And we jump right into an example. They say graph point A at 4, 150. Well, the x-axis is my starting off point, right? Is my beginning. It's the 0 degrees or the 360 if you want to consider going all the way around, right? So we would measure 150 degrees and then take 4 steps out from our center pole. 1, 2, 3, 4. So 4, 150 degrees is right there. That's how we do it. Now it says, reminder, lots of angles have coterminal angles, right? So we have to keep that in mind. Graph T at the point 4, negative 210. Now remember, they've got a lot more numbers on this one, and that's fine. But remember, when we go negative, we are not starting at our x-axis, our positive x-axis, and then going counterclockwise, right, like we normally would. When we're doing a negative 210 degrees, we go clockwise. So we're going to zoom down around here and then 4 points out. And that's our point T. They didn't label it this time, but that's where it is. All right. Over here, they want us to graph 6, 4 pi over 3. Well, we need to find our 4 pi over 3, which is here, and then count 6 points out from the pole. And that's where the dot goes there. Pretty standard, basic graphing. I don't feel like this is overly complicated, right? We get our ordered pair, we find our angle measurement, and then we count out the number of the distance from the pole being the center, right? The concept of an ordered pair is extremely important in plotting points in the rectangular coordinate system, and it is as well when we're graphing with the polar, right? When r is negative, now we're talking about r being our distance from the pole. When it's negative, the distance from the pole to the point is still the absolute value of r, but in the opposite direction. So looking at this example, graphing the point P at negative 6, 240. Okay, so we are still finding our 240 degrees, but instead of counting 6 points this way like we normally would, we're going to count 6 points this way. Okay, normally we would start here and go 6 points this direction where we would encounter, right, where we'd be at that 240, but because it's negative 6, we would count 6 points the opposite direction. And that is plotting our points. Now, this next part here is talking about converting coordinates. And what they're talking about is converting them from polar, which is r, theta, to coordinate, right? Rectangular is what they're going to call it, which is x, y. So it says drop a perpendicular from point T, right? If you dropped a perpendicular line here, you would get a right triangle, and we can do a lot of things with right triangles, right? So here are the formulas for going from polar to Cartesian, which is a rectangular, or Cartesian rectangular to polar, okay? Polar tells me that I already have the r comma theta, and they want us to change it over to x comma y. Here's how you solve for x. Here's how you solve for y. Cartesian tells me I have my xy already. So here's how I solve for r, which remember is my distance from the pole. And then here's how I solve for my theta. Okay, let's turn the page and see these in action. All right, the first column here on page 8 says to convert polar coordinates to Cartesian, use the fact that r times the cosine theta, comma r times the sine of theta is equal to x comma y, right? That's what was on that little chart that we just looked at. So here's our example. Find the Cartesian form for the point whose polar form is 2 comma pi over 6. Well, the solution here is 2 for the x is r times the cosine of theta. So 2 times the cosine of pi over 6, which the cosine of pi over 6 is the square root of 3 over 2. We might need to use our, for these exact answers anyway, we might need to use our chart. All right, so I grabbed my unit circle. Remember, this was from section 6 of book, oh shoot, what book was it in? Unit 2, I think. I think it's in book 2. Okay. Or you know, you have this chart that we use all the time from page 75 of unit 3. Okay. But I think this was in unit 2. Anyway, if we look at, let me set this back up. If we find pi over 6, you know, on our unit circle, it's right here, pi over 6, right? The cosine, because remember it's cosine comma sine, is square root of 3 over 2. So that's what they've put here. So 2 times the square root of 3 over 2 reduces to the square root of 3, right? To find the y, so that's my x. To find the y, it's r times the sine of theta. So 2 times 1/2, which is 1. So my coordinates on the Cartesian system, sometimes they call them rectangular coordinates, okay, is square root of 3 comma 1, right? So again, here's another example. Convert this polar coordinate, because we have a distance and a alpha, right, a degrees, to rectangular coordinates. Now they switched their vocabulary, but it's the same thing. Cartesian, rectangular, same thing. Again, we're going to do the same process, right? So my x is going to equal r times the cosine of theta. -5 times the cosine of 225 degrees. 225 degrees is here. The cosine of that is negative square root of 2 over 2, which is what they've put here. So becomes positive 5 times the square root of 2 over 2. Same thing for the y value, because this point has identical coordinates, right? So the y is 5 times the square root of 2 over 2. So that is our xy. Now, to convert the other way, to polar, so from rectangular or Cartesian is that they were using to begin with, right? To polar, we use the following fact, that the r, you could call it radius, I suppose, but remember it's the distance from the pole, is going to equal the square root of x squared plus y squared. And the theta is going to equal the inverse tangent, you know, we're going to use our calculator to switch it back, of y divided by x. So if we have the point 2 comma 2, now I don't know why they couldn't have just started the example up here so it was all in the same section, but that's okay. Convert the square, I'm just going to write it up here. We have the point 2 comma 2. Okay, to find r, we are going to take the square root of 2 squared plus 2 squared, which is 8. Square root of 8 is 2 times the square root of 2. Okay. To find theta, you're going to take 2 divided by 2, which is 1, and then the inverse tangent of 1 is negative, or is 45 degrees, okay? So the polar form is at 2 times the square root of 2, comma, 45 degrees. All right, let's look at another one. Converting the point -2, comma 3 to polar form. Well, we're going to take the square root of x squared plus y squared, which is the square root of 13. That becomes my r. To find our theta, we are going to divide 3 divided by -2 and then take the inverse tangent, okay? Now, it says using a calculator tells you that theta is approximately -56.3 degrees. But remember, our point, so -56.3 degrees would be over here in quadrant 4, right? Because remember, negative, we go clockwise. But remember, our point is -2, comma 3. That's going to be over here in quadrant 2. So we have to find the reference angle, and then we discover that it's actually 123.7 degrees. So be careful when you're doing this, that your measurement, when you find your measurement for your angle, it actually lands where our point is, okay? And that's that. Let me move this out of the way. Oh, that's it. So let's review. Tells me we're ready to do some of these problems together. So let's take a look here at problem number 2. It says graph the point having the polar coordinates 4, comma, 315 degrees. First thing we're going to do is we're going to locate our 315 degrees, right, which is right here. And then we're going to start at our pole, and we're going to come out 4 points. 1, 2, 3, 4. Okay, right here. Now, we do not need to draw an arrow that comes around to here, right? It's just a point. Graph the point. So it's literally just the point right here. That is the point. Okay? Let's turn the page and do some more. Let's take a look here at number 3. Number 3 is asking us to graph the point 2, comma, 4 pi over 3. Okay? So 4 pi over 3 is the first thing that we want to locate, which is here. Now, they have the pi kind of set off to the side, but it would basically be in the numerator if you were to actually multiply. So 4 pi over 3 is here. And the point 2 tells me I'm going to start at my pole, and I'm going to come out 1, 2 points. And there we have it. Okay? Now, don't read too much into the fact that it says graph the points, plural. I think it's just a misprint. Okay? Because I've looked into everything. I'm pretty sure it's just a misprint. All right, let's take a look here at number 6. We can do one of these negative ones. So, graph the points having the polar coordinate -4, comma, 240. So again, I'm finding my 240 here. So I would normally start at the pole and go towards my 240, right? But I'm going to start at the pole and go opposite my 240. Now, I have a bit of a, like, it's kind of hard for my eyes to focus on which line goes against the 240. So I'm going to use a ruler. Like, in here in this first thing, the lines are just too close together and it starts to blur for me. So for me particularly, I'm just going to use this line. If you don't need it, then by all means, don't use it. A little ruler here. Now, I'd be at the pole and I'd be going 4 points towards the 240, right? But since it's negative, I'm going to go 4 points in the opposite direction. So 1, 2, 3, 4. And my point is going to be here. Okay? So that's how we do a negative. Let's turn the page because there's some conversion problems I want to do together. All right, let's take a look on page 13 here at problem number 9. Express the polar coordinates -1, comma, 180 as Cartesian coordinates. Okay, again, so they're going back to Cartesian, but remember, if they use the word rectangle, it's the same thing. So just keep that in mind. So I grabbed my unit circle so I can, help use these little bits, right? And remember that when we're going from polar to Cartesian, we need to solve for our x, which is going to equal r times the cosine of theta, and my y, which is going to be r times the sine of theta. All right? So, that being said, we are going to solve for x first. So, x is going to equal -1 times the cosine of 180 degrees. My cosine of 180 degrees is a -1. So x is equal to 1. For my y, it's going to be -1 times the sine of 180 degrees, which is 0. So my y is going to be 0. So the point is at 1, 0, right? Which is letter D. Let's do another one. Number 10. Express the polar coordinates 2, 3 pi over 4 as Cartesian coordinates. All right, so x is going to be 2 times the cosine of 3 pi over 4. 3 pi over 4 is here. The cosine is negative square root of 2 over 2. So my x is going to be negative square root of 2, right? The y is going to equal 2 times the sine of 3 pi over 4, which is a positive square root of 2 over 2. So y is equal to square root of 2. So my point is at negative square root of 2, square root of 2, which is letter B. All right. Okay, let's jump down here to problem 14. In problem 14, it says express the Cartesian coordinate 0, 4 as polar coordinates. All right, so now we're going back the other way. Remember, to do that, we have, and I'm just going to squeeze it in right here, that r is equal to the square root of x squared plus y squared, and that theta is equal to the inverse tangent of y over x. All right, so let's take a look at what we have. For r, I'm just going to have to fit it in here. R is going to equal the square root of 0 squared plus 4 squared. Okay, or the square root of 16, because 0 squared is 0, 4 squared is 16. So it's going to be 4. So my r is equal to 4. My theta is going to be the inverse tangent of y over x, or 4 over 0. Now, the tangent is 0, right? So when we find the inverse tangent of 0, what is that going to give us? Let's grab my calculator. I believe it's on this other page, though, too. Yeah, right here. So the tangent of 0 is going to be 0, but let's just do it on our calculator so that we're all together now. So we have the second, or the shift tangent of 4 divided by 0. Close my parentheses. Oh, it says math error. Oh, yikes. So let's do the tangent of 0, because that's what that is 0. Okay. So theta is 0 degrees. So my coordinate here is at 4, 0 degrees, which is letter C. All right. Let's look at another one. Express the Cartesian coordinate -2, 2 times the square. I want to do, Cartesian. Let's switch it over to polar. Yeah, that's what we're doing. Okay. Sheesh. So r is going to equal the square root of -2, the quantity squared, plus 2 times the square root of 3, the quantity squared. Okay. That's going to be the square root. -2 squared is 4, right? -2 times -2. 2 times the square root of 3 squared is the 2 squared, which is 4. And the square root of 3 squared, which is 3, right? The square root of 3 times the square root of 3 is just 3. So this becomes 4 times 3, which is 12, okay? So it becomes the square root of 16, or 4. So we got a 4 again. My theta is going to be equal to the inverse tangent of y over x, right? So 2 times the square root of 3 over -2. So it's the inverse tangent of negative square root of 3, because our 2's cancel, okay? So second, or shift tangent, I am going to do negative square root of 3, close my parentheses, right? I close my parentheses around this 3 because that's what's in my square root. I have to close the parentheses around my tangent because I want all the tangent parts together. I know that circle light is in the way, I'm sorry. And then I hit equal -60 degrees. So theta equals -60 degrees. Now, we need to check, is that right? Where -60, remember, is going to be over here in this quadrant, quadrant 4. That's not what we want. Our point is at -2, +2 times the square root of 3. It's going to be over here somewhere. So 180 minus 60 gives me 120 degrees. So my point is at 4, 120 degrees. Okay, which is letter C. All right, they don't give us a lot of room to do these problems, so you might want to use scratch paper because this is definitely a bit clustered. But for recording purposes, it's easier to do it this way, right? Okay, that's this first part of section 1. Go ahead and finish the rest of these problems on your own, and then meet me back here for the next part. The next part of section 1 begins on page 14, and it's titled Polar Equations. Now it says converting Cartesian equations to polar equations. Cartesian equations contain variables x and y, and polar equations contain the variables r and theta. To convert Cartesian equation to polar form, begin by using the following equivalencies to make substitutions, the same ones that we just learned, okay? So if this is our, let's look at this first example. If this is our equation, okay, it's the equation of a circle, x squared plus y squared equals 4. They want us to change it to a polar equation. We are going to replace our x and our y with our r times the cosine of theta and r times the sine of theta, okay? They've distributed, or they've squared it, okay, which ends up being r squared times the cosine squared of theta plus r squared times the sine squared of theta equals 4. Then they pulled, or they factored out this r. They both have an r squared, so they factored out the r squared. So we're left with cosine squared of theta plus sine squared of theta. Now, cosine squared of theta plus the sine squared of theta is equal to 1, right? That's an Pythagorean identity, so they changed it to 1. Now, do not think that this is actual work that you need to do. We're just explaining how they get to where they're getting. So r squared now equals 4, or r equals 2. Because remember, in this equation of a circle, x squared plus y squared equals r squared, right? The radius of the circle squared. So technically, r squared equals 4, r is actually 2. And that's just what they've solved for here in a very, very complicated way. All right, much more complicated than we need to do. Basically, this is a circle with a radius of 2. But we knew that already just by looking at this, right? This is the formula for a circle. R squared is equal to 4, so our radius is 2. Now, that's basically all they're saying here as well, right? X squared plus y squared equals r squared is what this should be. That is the formula for a circle. So the polar equation, r is equal to 2. This should have a little 2 here. Otherwise, r would be 4, right? So it's r squared. All right, let's take a look at an example here. Problem we can actually do. Convert x equals 2, to polar form. So we're going to change it to the r times cosine of theta equals 2. They solved for r being 2 over the cosine of theta. Now, they say because the secant of theta is 1 over the cosine of theta, you can also rewrite this as 2 times the secant of theta. Okay? I don't know how useful that is, but our radius is 2 times the secant of theta. We don't know what the secant of theta is, but we know that x equals 2 is a vertical line, right? Is what they're saying here. X equals 2 is a vertical line no matter what. Our x is always going to be 2. That's what how a vertical line looks, okay? So now they want us to convert, for this example, x squared plus y squared plus 2x equals 0 to polar form. All right, well, they're again substituting x equals r times the cosine of theta for x, and y equals r times the sine of theta for y. Then they distributed their square, and of course they again pulled out their r squared, sorry. And that changed cosine squared of theta plus sine squared of theta to 1. They also changed this x, right? But we'll deal with that in a second. So from this part here, we're just left with r squared, okay? Because the formula is x squared plus y squared equals r squared. So we don't need to go through all of this. We could literally have just changed it right here. We could have gone from here to here, boop, 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 okay? This is a lot of work, and it's unnecessary. Now, for the x, or the 2x, they changed that x to r cosine of theta, right? Then distributed their 2, but I mean, it's just a 2. Goes out front. So that's just kind of been following along. So we are here after all those steps that were unnecessary. All we had to do was rewrite it from here to here, right? R squared plus 2r cosine of theta is equal to 0. Subtract that 2 from r cosine of theta from both sides, and then we have r squared equals a negative 2r cosine of theta. And then they divided by r. Because both of them have an r, it's not real clear here. You would think, oh, the next step is take square root. Because there's an r here, they divided both sides by r. And so that became, this became 1r, and then this r canceled out. And so now r is equal to negative 2 cosine of theta. Okay? Okay. These are kind of like, I mean, it says convert, but it's almost like simplifying it in a polar form, you know, using identities and stuff, but that is really unnecessary. This is a good identity to use. Okay. Converting polar equations to Cartesian equations. Now, converting a polar equation to a Cartesian or rectangular still requires the use of these that we've been using, but it also may be necessary to use the cosine and the sine. And here they are, right? Cosine is x over r, and sine is y over r. Okay? Let's take a look at this example here on page 15, the second column. Convert theta equals 30 degrees to a Cartesian equation. All right? Because they're only giving us pieces of things, right? They're not giving you all of the parts. It's why we're ending up with, oh, a secant and a cosine in the formula. Okay? Now, we have our theta. So because we actually know the measure of the degree, we can find out what the cosine and what the sine is. And so x and y are going to be equal to r times that number. Then they solved for r, right? So the x is now in, and the y is now in. So 2x over the square root of 3, and r also equals 2y. Now, because they solve for r in both cases, they can set these two pieces equal to each other, right? They can substitute it. This is equal to r and this is equal to r, so they must be equal to each other. And that's what they've done here. Then they got the y by itself because that's how we like to look at equations, right? So we want it to be y equals, so they divided both sides by 2, and they got x over x over the square root of 3. Okay. Now we can't have a square root of 3 in the denominator, so they simplified that out and got y equals x times the square root of 3 over 3, or the square root of 3 over 3x. Now, normally, this is the way you would see it when you are graphing something, right? Because we kind of pull the x out of the fraction and just have it sit there, because then we substitute points in and we graph it, right? So this is the normal form we would probably see it in, but if you left it like this, it's the exact same thing. These are identical, okay? And so our line is x equals the square root of 3 over 3, or sorry, y equals the square root of 3 over 3x, where the square root of 3 over 3 is the slope of the line, and it starts at the origin point. Okay, and even though it doesn't say to graph it, they graphed it here for you. All right, let's turn the page. All right, we've got a couple more examples, and then we'll do some problems together. Here it says convert r equals 2 to a Cartesian equation. Okay, well, remember, r is equal to the square root of x squared plus y squared, but here r equals 2, right? So x squared plus y squared must equal 2. They squared both sides to get rid of the square root, and they got x squared plus y squared equals 4. That's it. That's it. You're done. That is a circle with a radius of 2, which is what we already knew. So x squared plus y squared equals 4. Okay? Done. That one's pretty basic one. If they give you the r, it's pretty, well, this one is a little bit crazy, but that's okay. Not anything we can't handle. So this example wants us to convert r equals the tangent of theta to a Cartesian equation. Okay? They started with r equals the tangent of theta, which remember is the same as the sine over the cosine. Now, because we want it to look, remember, our x is equal to r times the cosine of theta, and my y is equal to r times the sine of theta. Because they want it to look like that, they multiplied this side of the equation by 1, or r over r. Okay, and so that's how they got from here to here. Because now these look like this, and they can change it to r equals y over x. Now here's where I differ from their process. Okay, they took this and solved for y. Okay, and then they squared both sides and got r squared times x squared equals y squared. I mean, it's the same process, I suppose. So we'll just follow through, and then I'll kind of show you what my thought process was. They substituted then x squared plus y squared for r squared because that is the same. They are the same. I know it's written somewhere right here, right? R squared is equal to x squared plus y squared. So they substituted that in for the r squared, and then they distributed their x and moved this y squared over. Okay, so my thought process here was that if r is equal to y over x, then r squared is equal to y squared over x squared, right? And rather than substituting or solving for y squared, right, because I feel like that's probably not necessary, I substituted here because I know that r squared is equal to x squared plus y squared. So x squared plus y squared is equal to y squared over x squared, right? R squared. This is r squared. Okay. I multiplied both sides by x squared. So x squared times the quantity x squared plus y squared is equal to y squared. And then I have x to the fourth plus x squared y squared. Okay, that's this distributed. And then if you move this over, because they want it all on the same side of the equal sign, minus y squared equals 0. Okay, same exact answer, slightly different method. You know, this is my thought process. Here's the book. Whichever way leads you, do that way. Whichever way you see it, and because obviously there's multiple steps, right? Different ways to get to the same answer, as long as you're getting to the correct answer, right? If you're not getting to the correct answer, then you need to go back and try to understand. Contact me and I can try to help you try to understand the process. Okay? All right. Let's look at this example over here on page 16, second column. Convert r squared equals 4 sine of 2 theta to a Cartesian equation. Well, and it says, remember, r squared is equal to x squared plus y squared, okay? So make a substitution for r squared, that x squared plus y squared is equal to 4 sine of 2 theta. Now, using a double identity, they changed the 2 theta over to 2 times the sine of theta cosine of theta, and then you could multiply the 4 and the 2. Now we have x squared plus y squared is equal to 8 sine of theta times the cosine of theta. Remember our x and our y again. Okay, these conversions here were, remember, at the bottom of the page right before here. Okay, cosine is x over r, sine is y over r. So, you know, it's important to note, because now we can change this sine and cosine over to x and y's, x's and y's. Okay. And then we multiply it out and we get x squared plus y squared equal to 8xy over r squared. Okay, so when we're, the point is when we're going from polar to Cartesian, we don't want any sines and cosines. We want only x's and y's, and vice versa when we're going the other way, okay? They multiplied both sides by x squared y squared to get it out of this denominator, and so they ended up with x squared plus y squared, the quantity squared, is equal to 8xy. Now, I suppose you could divide both sides by xy and have it equal to 8, so it's just a whole number, but the book says that's enough, then that's enough. All right? Okay, let's look at some of these problems together. I feel like they're not going to be as complicated as these last couple of examples, but let's take a look. Convert the Cartesian equation x squared plus y squared equals 16 to a polar equation. Well, remember that x squared plus y squared is equal to r squared, and the r is the only part that we are interested in. So if we substitute r squared for this part, we get that r squared is equal to 16. And so r is equal to 4. Letter A. Okay? I feel like the polar, or the Cartesian to polar is easier than the other way around, right? Let's look at 21. Convert the Cartesian equation x squared plus y squared plus 2y equals 0 to a polar equation. Okay. Again, remember, this is our base. So if we substitute r squared for x squared plus y squared, we get r squared is equal to, or not equal to, sorry, plus 2y is equal to 0. Now we need to change this y to something else. And remember, y is equal to r times the sine of theta. So r squared plus 2 times r times the sine of theta is equal to 0. So this is just 2r sine of theta, right? So r squared is going to be equal to, I'm going to subtract it from both sides. So negative 2r sine of theta. And then we're going to basically factor out an r from both of them. So r is equal to negative 2 sine of theta. Okay? Negative 2 sine of theta, it looks like letter B. Letter B. Okay, let's look at number 25. For number 25, it says convert the Cartesian equation, the quantity x squared plus y squared squared equals 4 times the quantity x squared minus y squared to a polar equation. All right, this is kind of a chunky problem. I am going to grab a little note paper here. Okay. I don't think it's going to fit in this little bit on the side, which I don't like to do normally because I like to keep it all together. But, you know, if you're using scratch paper, then that's what you would do too, right? So I'm going to rewrite the problem. X squared plus y squared, the quantity squared, is equal to 4 times the quantity x squared minus y squared. Okay, that's what we're working with. Problem number 25. All right, this side, fairly basic, right? R squared is equal to x squared plus y squared. So this is r squared, the quantity squared, or r to the 4th, right? We'll get that done right off the bat. No need to do the crazy amount of work they did to find that answer. We know those things are equal. There's our r, right? Our x and y are gone. We're trying to get to polar. We got to get rid of our x and our y, okay? This part is a little bit more complicated. Now, remember, my x is going to be equal to the r times the cosine of theta, and my y is going to be equal to r times the sine of theta, okay? That's what I'm going to substitute in here for now, because I need my r's, I need my thetas, right? So I'm going to have 4 times the quantity, r times the cosine of theta squared, minus r times the sine of theta squared, close my parentheses, okay? Now I'm going to distribute my square. So I'm going to have 4 times r squared times cosine squared of theta minus r squared times the sine squared of theta. All right. Now I'm going to factor out my r squareds. So I'm going to have 4r squared times cosine squared of theta, cosine squared of theta minus sine squared theta. Okay, that's where I'm at right now. Cosine squared of theta minus the sine squared of theta. Now, because we're having to use identities, right? This one, I'm like, oh, that sounds familiar. I don't remember it exactly. So I ran out and got my book 5, okay? And remember, in the back of book 5, it has all the identities broken out neatly for us. On page 45, we see that cosine squared of theta minus sine squared of theta is equal to the cosine of 2 theta. So that's our substitution now. So 4r squared times the cosine of 2 theta, all right, is equal to r to the 4th. All right, so now we're getting closer. All that there's left to do, right, is divide both sides by r squared, because I want to cancel this. And so I'm left with r squared is equal to 4 cosine 2 theta. All right, a little bit of gymnastics on this side, I gotta say. But we did it, right? Together, we worked through it. The letter is B, answer B. Okay, I gotta write down what problem this is. 125, page 17. All right. That way I can keep it. I got to get a paper clip and stick it in there. All right. What is the slope of the line whose polar equation is theta equals 60 degrees? Okay. Theta equals 60 degrees. So this is the kind we need to switch over from polar to Cartesian. And that will give us our slope. I'm going to use scratch paper for this one as well, because I want to make sure I cover everything. All right. So our theta is equal to 60 degrees, right? Remember that our x is equal to r times the cosine of theta, and my y is equal to r times the sine of theta. Okay, so x is going to be equal to, oh, 1 second. All right, now we're back in business. X is equal to r times the cosine of 60 degrees, and y is equal to r times the cosine, or times the sine of 60 degrees, okay? The cosine, let me grab my unit circle, 60 degrees is here. So the cosine, so x is going to be equal to r times 1/2, right? And y is equal to r times the square root of 3 over 2. Okay, all of these things are useful. I know it's kind of a pain in the butt to keep the other books we've already finished just sitting around, but they're always going to be useful to go back and review, or if you're making photocopies of stuff, keep it together in like a little folder, a binder of all the useful information that we need to keep using. Yeah, I mean, it's just what it is. All right, so I'm going to rewrite it because I kind of wrote this a little bit weird. So r is equal to, or x, sorry, is equal to r times 1/2, and y is equal to r times the square root of 3 over 2. All right, remember, we want to solve for r. So to solve for r, we're going to multiply by the reciprocal, or by 2 on both sides. Right, these cancel. So r is equal to 2x. On this one, we're going to multiply by the reciprocal, 2 over the square root of 3. So that 2 over the square root of 3. Okay, so that here r is equal to 2 over the square root of 3y. All right, I'm just going to leave the y on the outside for now because we can't have a square root of 3 in the denominator, right? So we're going to have to multiply by the square root of 3 over the square root of 3. And so this kind of ends up being r is equal to 2 times the square root of 3 over 3y. Now we set them equal to each other. So 2 times the square root of 3 over 3y is equal to 2x. Okay, and now we have to get the y by itself. So again, we're going to multiply by the reciprocal, which is 2 times the square root of 3. Okay, so these cancel, right? So over here we have a 3 over 2 times the square root of 3. Now for here, my 2's are going to cancel, so that y is equal to 3 over the square root of 3x. But again, I can't have the square root of 3 in the denominator, so I'm going to multiply by 1 in the form of the square root of 3 over the square root of 3. I hope I'm on screen still. I don't know. Okay, we're on problem 26. And so therefore, y is going to be equal to, okay, 3 times the square root of 3 over 3x, or y is equal to square root of 3x. Whew. Okay, that was kind of crazy. Now, all they're asking for is the slope. And remember, the slope, y equals mx plus b. The slope is the coefficient of the x. And so that's letter B. All right. Wow. Okay. Go ahead and work on these. Take your time. If necessary, especially for these couple that I left for you, you might have to go back to book 5 and look at some of those identities. All right, but go ahead and work on these and meet me back here for the next section. Or not the next section, the next part of this section. So the next part of this book is on page 19. It's called Polar Curves. And while I've gone through it and read it all and looked it over and done the work, you know, I've decided that this piece of section 1 is I'm going to omit. I don't really see a value in it. I mean, some of the stuff is pretty cool looking, but there isn't really math necessarily being done here. It's kind of like, oh, you know, what would this graph look like? What would this graph look like based on this information? I feel like you could graph it as on a graphing calculator and find that information. I don't see value in this part of this section. So, because technically when you do a curriculum, right, in the public school system, in the school system, they say 80% of the book is all that needs to be done. We consider all of these books to be a book, right? So if we only did 8 of the 10 books, we'd be doing 80%. So skipping one little part is not going to kill us. If you are one of my online viewers and you really, really want me to go through this, let me know and I will post a video about this section. But for my classroom students, we are not going to be doing this, so I'm going to now skip ahead to page 26. All right, this is the last part of section 1. It begins on page 26, and it's called Polar Forms of Conics. All right, let's take a look at what that means. There's obviously some vocabulary. Make sure you review that. It says, when a plane intersects a cone, conic sections are formed. And so what that means is if you have a cone, and I'm not great at three-dimensional shapes, so keep that in mind, right? Here's my cone. And a plane being just like a slice of paper, right? It intersects it. Now it can intersect it at different pitches, right? At different slopes. But as it intersects it, it kind of slices that cone shape into different shapes. Now, if it slices it on an angle, it's going to be more elongated. If it slices it perpendicular to the base, it's going to be a perfect circle, right? So there's different places and different ways it gets sliced, and that's what all of these are. That's what this means. Okay, conic sections are formed. These conic sections can be defined by a set of points and their distance from a fixed point, and or a fixed line. The parabola is the locus. Now, a parabola would be if the plane came and cut it like right this way. Okay, so you're not actually getting all the way through cut, but you're going to be left with a swoop, right? Okay, so the parabola is a locus of points in a plane for which the distance from the fixed line, the directrix, here's my directrix, a fixed line, and a fixed point called the focus are equal. So my directrix is here, my focus is here, it doesn't move, right? But as we move up here, the distance, so say my point here was here, the distance from the focus and the directrix would still be equal. That's what makes the parabola the shape that it is, okay? Or that's how they defined its shape, all right? So that's what this means. The focus, point distance from the focus and the directrix at any point on this parabola is exactly the same, right? An ellipse, which is probably more like this slice that I took, you know, in my original example, is the locus of points for which the sum of the distance from two fixed points is constant. So now we have two foci, and the distance is going to be equal, or not equal, constant. So this plus this is a constant number. No matter which point you have around this ellipse, it's always going to be, if this plus this was 7, let's say, no matter what point you picked, the two distances should add up to be 7, okay? And a hyperbola is the locus of points for which the difference of the distances from two fixed points is a constant. Now, a hyperbola is two, basically like two parabolas, right? Basically. Okay. Hyperbola is formed when we have two cones like stacked on top of each other, okay, which is a whole nother, it's whatever. Okay, is the locus of points for which the difference of the distances from two fixed points is constant. So now we're subtracting, right? Distance 1 minus distance 2 is always going to be the same. All right, now the eccentricity E of a conic section is positive constant, which indicates its general shape. If E is 0, the conic is a circle. If E is less than 1, the conic is an ellipse. If E is equal to 1, the conic is a parabola. And if E is greater than 1, the conic is a hyperbola. Now, they derive the polar form, which, you know me, I'm not super keen on following all of the steps of the deriving. But we need to look at the top of page 27 here, where it says the eccentricity is defined as E equals the segment from the focus to the point over the segment from the point to the directrix, or any one of these, right? That is how we find our E. And then they solve for FP, okay, from the focus to a point, and they do a lot of things, all right, to derive. As you can see, they do a lot, okay? But it leads us to the polar equation of conic sections with the focus at the pole. Now remember, a pole is the origin point, right? So if R is equal to ED over 1 plus E times the cosine of theta, then the directrix is vertical and to the right of the pole, okay? So if we're looking at our pole, right, the directrix would be vertical and to the right of the pole, so it'd be on this side. If R is equal to ED over 1 minus the cosine of theta, or E times the cosine of theta, then the directrix is vertical and to the left of the pole. If R is equal to ED over 1 plus E times the sine of theta, so cosines, we have vertical directrix, one side or the other, right? A positive to the right, a negative to the left. If we have sines, because the formulas are basically similar, that being the difference, then the directrix is horizontal, positive being above the pole and negative being below. All right, this is obviously something we're going to need to use moving forward. All right, turning the page. Praise Jesus, they repeated it right here, so we don't have to worry about copying it over right now. But let's take a look at some of these examples, okay? Given the polar equation r equals 3 over 2 plus 3 times the sine of theta, determine the type of conic section, its eccentricity, and its directrix. Okay. Let's figure out what our parts of our formula are, because remember, here's our formula. And so it's E times D is in the numerator. So E times D equals 3, D being our directrix, okay? And here I have just E times the sine of something, right? It's this one, because this is the one we're dealing with. But here it's supposed to be E times the sine. So E is equal to 3. So if E equals 3, then D must be 1. Has to be, because this is a 3 up here as well. Okay? That's really what they're wanting us to know. Or that's really what they want to know, right? Determine the type of conic section. Well, my E is a 3. So it is greater than 1, so it's a hyperbola, right? Although I don't, oh, right here, hyperbola, okay? It's a hyperbola. Or my E is greater than 1, it's a hyperbola. They want us to determine its eccentricity. We did that already. It's 3, because that's the only thing it can be. Okay, I see where I'm a little bit off here. So this is supposed to be a 1. That's why they've divided by 2, okay? So our E becomes 3 over 2. Our directrix is still a 1, but this time our E has to be 3 over 2. I get it, okay. Which is still greater than 1, which still makes it a hyperbola. I just don't want us to be off on our eccentricity is 3 over 2, technically, because to have it be in this form, right, this has to be a 1. And that's why they divided by 2. And then it asks the directrix. The directrix is at D equals 1, which is technically Y equals 1, because when we are dealing with this, remember, the line is horizontal and above the pole, so it'd be Y equals 1. Okay, let's look at another example. This example here says, write the polar equation of the conic section with its focus at the pole and an eccentricity of 1/2, and a directrix is r times the cosine of theta equals 3. So remember, r times the cosine of theta is the same as x. If x equals 3, and I'm just going to borrow this just as an example, right? X equals 3, then my directrix is vertical and to the right, okay? So vertical and to the right is this form, right? And so that's the form they've started with, okay? My E is 1/2. My directrix is 3, so it becomes 3 over 2. Now, to get rid of the fraction, they multiplied it by everything by 2, and so it's 3 over 2 plus the cosine, and that's the final answer, okay? One more example here. Identify and graph the conic whose equation is r equals 5 over 2 minus 2 sine of theta, right? Again, they're going to divide by 2 to get the denominator to begin with a 1. So we end up with 5 over 2 over 1 minus the sine of theta. So looking over here, 1 minus the sine of theta is this form. It is a horizontal, the directrix, sorry, is horizontal, and it's going to be below the pole. The directrix is down here, okay? That much we know. We know that E is equal to 1 because there's nothing here, right? There's no coefficient technically before my sine, so E is equal to 1. If E is equal to 1, this is a parabola. So that's what we know for now. If E is equal to 1, then my directrix is at 5 over 2, but it's below the pole, okay? So, okay, if our directrix is below the pole at 5 over 2, remember that's a distance. So 5 over 2 below the pole is 2.5. So 1, 2.5. I like to actually show my directrix is on my graphs, so I would put it in as a dotted line, okay? Now, to find the pole, because they want you to graph this, right? Remember, if it's 5/2 below the pole, okay, then your focus, or your vertex, sorry, is, your focus is the pole, but your vertex is going to be halfway in between there. So if you take 5/2 times a half, you get 5/4, and that's where they put their vertex, and then they've just done a basic graph, okay? Okay. This and this, super useful for these types of problems. Definitely information we want to keep at hand. All right, we're going to turn the page and do some of these problems together. Okay, we are on page 30 looking at problem number 59. Now, the test is kind of in the middle. I just folded it over so you can see that there's actual more homework to do on page 31. All right, but page 30, we are looking at problem number 59. It says, what is the directrix of the parabola by the given equation? R equals 2/1 plus the sine of theta. Now, I went ahead real quick and made a photocopy of page 29 so that I could have the information here. I got to cut this part off. I guess I don't really need it. So back to the problem 59, they want to know what is the directrix. Now remember, the directrix is the D. We have 1 plus the sine. It really does not matter, except the fact that E is the coefficient of the sine, right? And E is 1, so my directrix has to be 2. The directrix has to be 2, because that's, right? E times D is equal to 2. If E equals 1, then D must be 2. So D has to equal 2. Now, that doesn't give us a proper answer over here, right? Remember, though, we have 1 plus the sine. So it's this one. The directrix is horizontal and above the pole. So horizontal tells me that it's a y, right? And so y equals 2. Again, still doesn't give us our answer here, right? But remember, because the book likes to be crazy, y equals r times the sine of theta. So r times the sine of theta is equal to 2. Letter A. Right? They took a simple question and made it kind of hard. Not, the question wasn't hard, but the answer that they wanted was not straightforward. Anyway, let's look at number 60. Identify the eccentricity of the conic section whose equation is r equals 3 over 5 minus 3 cosine theta. Okay, we've got to get this 5 to be a 1, so we have to divide everything by 3. So I'm going to have 3 over 5 over 1 minus 3 over 5 cosine theta. They want us to solve for the eccentricity. Remember, the eccentricity is always the coefficient of our theta down here, right, as our trigonometric thing. So our eccentricity is 3 over 5. 3 over 5, letter A. Let's do one more of these, and then we'll take a look at page 31. Identify the conic sections whose equation is r equals 1 over 2 minus 3 sine of theta. Now, before we divide by 2 and whatever, it's a 1 minus sine of theta, okay? 1 minus sine of theta is here, and well, I suppose we have to do the division to figure out our eccentricity, to figure out what kind of thing. So if we divide by 2, we get 1 over 2 over 1 minus 3 over 2 sine of theta. 3 over 2 is greater than 1, right? Because that's 1.5. Greater than 1 is a hyperbola, which is letter C. All right? Okay. Let's flip over and take a look here at page 31. Move this test out of my way. And let's take a look at problem number 64. Write the equation of the conic section satisfying the given conditions. Focus at the pole. Okay. E is equal to 3/4. a horizontal directrix 2 units above the pole. So I'm going to just draw a quick, here's my focus. 2 units above the pole is my directrix. Okay. It's just giving me an idea of what I'm looking at. And my E is equal to 3/4. So horizontal directrix, it is going to be one of these two, right? The horizontal is above the pole, so it's going to be this one. So R equals ED over 1 plus E sine of theta. That's the formula we're working with, okay? Let's fill in the information that we know. So E is 3/4, and my directrix is 2 over 1 plus 3/4 sine of theta, okay? I'm going to leave the 4 for now, so this is going to become, this top here is now 6/4. We're just going to leave it like that for now, okay? 6/4. I need to get rid of the fraction down here, so I'm going to multiply all the terms by 4. So when I do that, I end up with R equals 6 over, and that's why I left it that way, 4 plus 3 sine of theta. Okay, so R equals 6 over 4 plus 3 sine theta. And that is the equation that would be there. Okay, let's take a look at this. Choose the graph of the conic sections whose equation is 20/5 minus 4 sine of theta. Okay, I'm going to divide by 5. 20 divided by 5 is 4. I mean, you can kind of see what's happening. They're all ellipses, right? But I want to be sure that this is going to be 1 minus the sine of theta, okay? Because I'm not dividing by 4, I'm dividing by 5. So not 1 minus. It is going to be 4/5 the sine of theta. Okay, divided by 5. I still have a 1 minus, right? 1 minus sine is this. Directrix is horizontal and below the pole. Okay, directrix horizontal and below the pole. So it's definitely not this one, right? Because it would just be like passing through it. So it's not B. And then these two are facing the wrong direction for this directrix, right? So the answer is C. Not super scientific answer, but it's the answer just the same. All right? Okay. Keep your notes with you, right? We're stacking notes, but that's okay. We're on book 7. We're coming on the finish line. We can do this. All right. Go ahead and finish the rest of these problems. That is it for section 1. Okay. As always, if you have any questions, or like I said, if somebody out there really, really wants me to do that piece that I skipped, let me know in the comments. Otherwise, until next time.